Imagine for a moment the sort of silent engine running behind every AI breakthrough, every new gadget, every single chip. It's not really the silicon itself, but this incredibly complex software that actually designs it. Welcome to our deep dive into electronic design automation, or EDA. You can think of it as like the ultimate productivity suite for chip designers, maybe like a superpowered Excel or Figma, but for engineers building the literal brains of our digital world.
That's a great way to put it. Yeah.
Yeah.
So much of the sheer complexity in designing modern chips, it's managed by EDA software. Without these tools, the kinds of chips we rely on now, they just wouldn't even be possible. It really is the hidden infrastructure, the foundation for the AI era,
Yeah.
for all this semiconductor innovation.
Right. So, our mission today is to unpack this hidden but absolutely vital technology. We want you to get a real shortcut to understanding this crucial layer beneath the AI hype. We'll dig into some surprising facts, hopefully, have a few aha moments along the way. We're drawing on insights from the real pioneers here, including the founding CEO of Synopsys, Aart de Geus, and their current leader, Sassine Ghazi. They're behind this, what, $80 billion company now.
It's remarkable. And what's really fascinating, kind of mind-bending, is that none of the AI applications we talk about today would even exist without the kind of optimization EDA provides. And now Synopsys itself is actually using AI to help design the software that designs the chips. It's gone full circle.
Okay, that really sets the scene. So EDA is this essential software managing complexity and making new chips possible. What about Synopsys' specific role? Where do they fit in?
Well, Synopsys is one of the two sort of giants in this space, them and Cadence Design Systems. They are absolutely fundamental to the whole semiconductor value chain, the whole ecosystem. I mean, when you talk about how a modern chip gets made, Synopsys is just woven right into that fabric.
It's incredible. And to think a company that critical, that fundamental, had to start somewhere. Let's go back a bit to the mid-'80s. Sounds like a pretty interesting, maybe challenging time for semiconductors.
Oh, absolutely. Yeah, the mid-'80s were rough. 1985 in particular was the worst downturn of the decade for the industry. It hit the big players hard, companies like General Electric. GE had actually invested a lot in semiconductors. They called it their factory of the future. But, it wasn't really their core thing.
Okay, so in that difficult climate, this amazing story starts. A small team at GE, led by Aart de Geus. They're facing layoffs, and they had this rebellious idea. What happened there?
Yeah, exactly. Rebellious is the right word. They'd built these really innovative design tools for GE's internal use, right? And rather than just let that work disappear as the division potentially wound down, they pitched this idea, let us spin this out as a startup, and, corporate spin-out succeeding, that's pretty rare. But GE actually supported them. They transferred the technology, which was valued at maybe $1 million then.
Wow.
Yeah. And then fast forward to the Synopsys IPO, that initial support, it turned into something like $23 million for GE. So quite a good bit of foresight, or maybe just a fortunate turn of events.
Okay, so what was that core technology, the thing they spun out with? What made it so groundbreaking?
The big breakthrough was something called synthesis. Before that, designing circuits was very manual, almost like an architect drafting blueprints. Synthesis, though, was software that could automatically design parts of the circuit based on a high-level description. They have this program at GE called Socrates that did this.
Socrates.
Yeah.
Okay. And the stories about early customer reactions, they sound almost mythical. You mentioned disbelief.
Oh, completely. I mean, imagine this. A customer gives them a circuit block, something they've maybe spent weeks, months, sweating over, tweaking manually. Synopsys runs it through their prototype tool, and in a few hours, they hand it back, saying, here you go, it's 30% smaller and 30% faster.
Just like that.
Just like that. The initial reaction was, no way, impossible, what did you break? Thought it was like some kind of trick.
I can only imagine. Pure magic, right?
Pretty much. But then they take the results back, spend weeks verifying them, checking every detail, and realize it actually worked. And that's when they didn't just become customers, they became partners. Their feedback was absolutely crucial in refining the tool and making it robust. And this marked a really profound shift. The field used to be called CAD computer-aided design. The software helped the human.
Right, it aided them.
Exactly. But Synopsys helped usher in EEA, electronic design automation. The software wasn't just aiding anymore, it was automating. It was changing the circuits itself. It was such a radical concept, the trust involved, that they actually had this internal moniker for it, giving the software a license to kill.
A license to kill. Wow. That really captures the shift, doesn't it? It's not just assistance, it's trusting the tool to fundamentally alter, hopefully improve your work. What a huge leap for engineers.
Massive leap. Because before, if a tool changed your design automatically, the assumption was, uh-oh, it probably introduced a bug. With synthesis, the tool was actually improving the design, making it better. That fundamentally altered the trust equation in chip design.
Okay, speaking of that engineer's journey, let's bring in that user perspective. You mentioned your own background. When did you first bump into Synopsys tools?
Yeah, so my first real encounter was during my master's and PhD work in VLSI design. That's very large-scale integration. Basically, the whole science of cramming billions of transistors onto a chip.
Yeah.
As we were, building design blocks, creating libraries of components, their synthesis tools were right there. They were becoming pretty central to the process even then.
And in your early career, say, when you were at Intel, what were the big roadblocks? What were the limitations in design, and how did you see the tools evolve?
Oh, back then, a huge bottleneck was just the capacity of the software. Seriously.
Yeah.
There were hard limits on how large a chunk of a design one engineer could realistically synthesize or simulate because the tools just couldn't handle more complexity, or it would take forever to run. And, even after you use synthesis, it was still pretty common to do a lot of manual checking, manual verification of the physical layout the tool generated. That was painstaking stuff.
Yeah.
We also saw this big shift in what we were optimizing for. Initially, it was all about performance.
Get it faster.
Speed was everything.
Speed was king. Then power consumption became critical, so it was performance and power. Now you're juggling performance, power, and area, how small you can make it all at the same time. It's this constant three-way balancing act.
That sounds like that license to kill idea, that leap of faith, really set the stage for something like AI coming in later. Given how cautious engineers were initially, how did that trust evolve when AI actually started showing up in EDA tools, maybe around 2018 or so?
Yeah, it's a really interesting parallel because even when Synopsys introduced AI, first for synthesis and then for place and route, that's the incredibly complex task of physically arranging and connecting millions or billions of components on the chip. There was definite resistance. For maybe the first 2 years, there was a tangible lack of trust, even though the AI tools were consistently producing better results, better power, performance, area, what we call PPA.
So engineers were still skeptical, even with proof. They were. And understandably so, right? They'd ask, okay, it's better, but what did it change? They wanted to understand the AI's decisions, even though tracking millions of automated choices is, well, impossible for a human.
So it's still kind of trust but verify, even with AI.
Exactly.
Yeah.
We actually joke about that internally,
yeah.
learning from Ronald Reagan. Trust but verify. You need the AI for the sheer scale of optimization, but you absolutely rely on massive simulation and verification afterwards to guarantee correctness. The value of trust is immense, but verification is non-negotiable. Because the cost of sending a chip to manufacturing with a bug is just astronomical. Millions, potentially hundreds of millions, down the drain.
That need for absolute correctness really highlights a difference from, say, generative AI that many listeners might be familiar with, which can sometimes hallucinate or be maybe 90% right. How is the AI in EDA fundamentally different? What are those unique challenges with that zero error requirement?
That's a really key point. The AI in EDA isn't generative in the sense of creating something entirely new from scratch with probabilistic outcomes. It's primarily tackling these massive optimization problems. You've got billions of components, incredibly tight constraints on power, speed, size, heat, things a human brain just cannot juggle at that scale.
Yeah.
The absolute critical difference is that requirement for absolute correctness in functionality, zero error tolerance. If you violate even one tiny design rule, your yield, the number of working chips you get from a wafer, can drop to zero instantly. So the AI has to operate within these incredibly strict boundaries. It's built on decades of accumulated knowledge about physics, materials, design rules. It's not just throwing a generic AI model at the problem. It's highly specialized, highly constrained optimization.
This brings up something important then. People often talk about Moore's law like it's, a law of nature, like gravity, something that just happens. But based on what you're saying, it's not like that at all, is it?
No, absolutely not. Moore's law started as an observation, sure, but it quickly became this, self-fulfilling prophecy,
Yes.
an industry roadmap, a race. And that race, it literally depends on companies like Synopsys getting clever again and again and again. Every single time the industry makes another leap, stays on that curve, it's because someone, somewhere in eDay, in manufacturing and materials, figured out how to overcome what looked like an impossible barrier just a few years before. So in a way, you could say eDay companies are a cause of Moore's Law continuing, not just a result of it.
And Synopsys's contribution to keeping that exponential curve going. What kind of scale are we talking about in terms of productivity improvement?
Oh, it's huge. We estimate our contribution over the decades is something like 10 million X in productivity for chip designers.
10 million X.
Yeah, to stay on that kind of exponential improvement curve, you have to innovate relentlessly. You have to race like crazy. And the secret, you race with customers who are even crazier, even more demanding than you are.
That phrase Aart de Geus used, thankful but never happy. That sounds like a tough dynamic, but maybe essential for driving that constant innovation.
That nails it. That's the core dynamic. They are constantly pushing the limits of what's possible. They need the next impossible thing yesterday. And that demanding relationship, that's what fuels the breakthroughs. What's also interesting, just historically, is how interconnected this all is. TSMC, the giant foundry, founded just 3 months after Synopsys.
No kidding.
Yeah. And
Well,
TSMC's very first CEO, Jim Dykes, he was actually Aart's general manager back at GE. It's a surprisingly small world, like one big, slightly dysfunctional, high-achieving family enterprise.
and those early relationships must be incredibly deep. You mentioned early customers like Chris Malachowski and Curtis Prime from Sun Microsystems, who later went on to co-found NVIDIA, right? And obviously the partnership with Jensen Huang at NVIDIA today. It sounds like Synopsys is truly mission critical for them.
Absolutely. I mean, when Jensen Huang himself says publicly that Synopsys is mission critical to NVIDIA's success,
Yeah.
well, you take that very seriously. It's a massive responsibility. We have to keep pushing the boundaries so they can keep architecting and building the amazing things they do. It's this constant three-way dance. Us, the chip designer customer, and the foundry, all collaborating on the architecture, the physics, the manufacturing, the software, bringing it all together.
Okay, so that brings us to where things are heading now. It sounds like we're moving beyond just shrinking transistors. We hear terms like the march to angstrom alongside the march to trillion. What do those mean? What are these paths forward?
Right. Those represent sort of the two key frontiers now. The march to angstrom, that's continuing the traditional path, shrinking transistors down to angstrom-level dimensions, pushing fundamental physics. But the march to trillion, that's about getting to astronomical transistor counts, maybe 1 trillion transistors in a single package, but not necessarily on one single piece of silicon. It's achieved through these new multi-die architectures.
So we're not just shrinking anymore, we're building things differently, connecting multiple pieces together. What's driving that?
Exactly. It's largely driven by what we call software-defined architectures. Basically, the workload, the software application, now dictates the hardware design. Think about GPUs, right? They emerged because standard CPUs just weren't good enough for graphics. Now, scale that thinking up. For something like a self-driving car, you need specialized processing for sensors, for path planning, for real-time AI. It's not one chip. It's a complex system of specialized accelerators. You're building a custom machine for the job.
And that leads to splitting the job across multiple smaller chips or chiplets.
Precisely. You break the functionality down into multiple dies or chiplets, and then you bring them incredibly close together, connecting them with super high bandwidth, very low energy links. NVIDIA's Blackwell GPU is a perfect example. They use this silicon interposer to basically stitch two large dies together, allowing data to fly between them almost as if they were one chip. That's how you get to these massive transistor counts.
It sounds like this also means running into new kinds of physics problems, not just manufacturing hurdles. You mentioned things like heat.
Oh, absolutely. Just shrinking isn't the whole story anymore. You hit fundamental physics walls. Thermal management is huge. When you pack billions, soon trillions, of transistors so densely, the heat they generate is immense. Managing that heat, preventing hot spots, avoiding physical stress that could cause the chip package to warp or even crack. These are now first-order design problems. You have to simulate and account for this stuff during the design phase, using multi-physics simulation. It's not just an afterthought.
So this must drastically change how you work with the foundries like TSMC.
Profoundly, yeah. Maybe 6, 7 years ago, our relationship was more about enablement. They'd give us the specs for their new manufacturing process, and we enable our tools to work with it. Now, Our engineers are sitting down with the foundry process development team, sometimes years in advance. It's co-invention, co-optimization. We have to figure out solutions together because just enabling after the fact isn't enough anymore to overcome these physics challenges.
And that sounds like what the industry calls DTCO design technology co-optimization.
That's exactly it. Optimizing the chip design and the underlying manufacturing technology in tandem. They deeply influence each other now. And looking ahead, take EUV lithography the tech used to print the tiniest features. Does it have more mileage? Yes, definitely. But will engineers find new ways beyond or around its limits eventually? Absolutely. Look at FinFETs, the 3D transistor structure. People once said that was impossible to manufacture reliably, especially for demanding things like automotive chips. But engineers find a way. That's what engineering is working around the perceived limits of science to make things happen.
So, okay, if simple scaling is hitting physical limits, what comes next? Where does the complexity battle move for Synopsys and the industry?
Well, once you hit those kinds of boundaries, what takes over is systemic complexity. It's not just about optimizing the transistor anymore. You have to understand how everything interacts, from the transistor physics to the chiplet connections to the software running on it, all the way up to the entire system architecture, like in a car or a data center. It's layers upon layers.
Hmm.
And another fascinating aspect tied to Synopsys' history is how globalization actually drove the need for these complex chains of collaboration. You couldn't just do everything in one place anymore.
Mm.
So that ability to build trust, to collaborate effectively across teams and companies became a really core skill.
Yeah, and does that tie into how the market itself has changed? You mentioned moving from a technology push to more of an end market pull.
That's exactly right. The pull from the big end markets, driven by massive trends like big data, AI, electrification, IoT, it's incredibly powerful now. Our software, our IP, it's not just a tool cost anymore. It directly impacts our customers' ability to compete, to differentiate their products, their P&L. We're not just selling shovels. We're helping them design the gold mines, if you like. It's a much more strategic partnership.
And this pull has apparently blown up your customer base way beyond the traditional chip companies, right? It's an amazing statistic that, what, 8 of the top 10 companies by market cap now design their own chips, and almost half your revenue comes from these system companies?
Yeah, 45% from system companies, OEMs making the end products, not selling chips directly. It's a fundamental shift. Think about the automotive industry again. The car makers, the OEMs, they're hiring their own chip architects now. They might not fabricate the silicon themselves, but they need to define the architecture, the electronic system of the entire vehicle. They use our software to design and, crucially, to virtualize that whole system, simulate how it will behave long before any hardware exists. Especially with electric vehicles and autonomous driving, the electronic complexity is just exploding. It's a massive and really exciting new area for us, virtualizing these incredibly complex systems.
This whole evolution, thinking beyond the silicon to the entire system, seems to lead directly to the huge news from earlier this year, the plan to acquire Ansys. What's the core thinking, the strategic logic behind bringing these two giants together?
Yeah, it's a big move, driven by two main strategic thrusts, really. First, it's about deepening our core business, tackling those Moore's Law challenges we talked about, designing those advanced chips, the multi-die systems. It's not just an electronics problem anymore. It's deeply intertwined with physics managing heat, stress, electromagnetics. Ansys is the clear leader in simulating those multi-physics interactions within the chip and package.
Okay, so addressing the physics on the chip itself.
Right. And second, it's about that system-level view.
Mm-hmm.
Those system companies, the car makers, aerospace companies, industrial equipment makers, they need to design and simulate the entire product, a digital twin of a car or a jet engine. Ansys is also the leader in multi-physics simulation at that scale. So bringing Synopsys and Ansys together creates the potential for this comprehensive design solution from silicon to system.
And Ansys brings this incredible legacy, this reputation for trust in simulation, doesn't it? Decades of experience.
Hugely important, yeah. They have over 40 years of accumulated knowledge baked into their tools. They are widely seen as the trusted simulator. When Ansys gives you a result, particularly for things like structural integrity or thermal behavior, there's a high degree of sign-off trust. Engineers rely on it to make critical decisions. And as compute power gets faster, partly thanks to chips designed with our tools, and as AI techniques improve simulation, it becomes practical to simulate more and more complex things. You can move away from costly, slow physical prototyping and testing towards virtual validation, towards digital twins. Ansys is key to enabling that future with confidence.
We've spent a lot of time on the tech, the processes, the strategy, but let's circle back to the human side. Synopsys doesn't just appear. Who are the people driving this constant innovation?
That's so important. Synopsys is first and foremost a collection of people. That cumulative learning, that 10 million X productivity gain, it comes from people. It's greatly helped by having many employees who've been with the company for a long time carrying that knowledge, combined with constantly bringing in new talent, new ideas. It requires continuous rejuvenation. There's this unique recipe, I think, a real passion for making the future possible, for tackling these impossible problems. But it's grounded in what Aart de Geus calls utter paranoia. The Andy Grove, only the paranoid survive mindset. Always assuming someone else is about to leapfrog you. And underneath it all, a deep belief that the impossible can be invented if you're smart and persistent enough.
Passion and paranoia, that's quite a mix. And how has the company's view of its own role in the world changed as it's grown so influential?
It shifted significantly. I
Mm.
mean, from being, just a tech tool company to becoming something more like, well, maybe a human company sounds a bit much, but certainly a company with broader responsibilities. There's a growing expectation, externally and internally, for influential companies to be value centers of gravity, especially now with all the geopolitical stuff, concerns about energy use. Our industry's energy footprint is projected to grow massively, maybe 10x climate change. You can't ignore these things.
Right.
Our internal philosophy has kind of evolved. It started as they who have the brains to understand should have the heart to help, which meant, being good corporate citizens, helping our communities.
Yeah.
But more recently, it shifted towards they who have the brains to understand should have the courage to act. That implies something more proactive. Not just empathy, but actually applying our unique capabilities, our engineering mindset, to help tackle some of these big global challenges. That definitely wasn't the original business plan, I can assure you. But it feels like a natural evolution, given the role we now play.
What an incredible story we've traced today. I mean, from that small, almost accidental GE spin-out facing layoffs to becoming this absolutely essential enabler of the entire digital age, the AI revolution. It's quite something.
It really has been an extraordinary journey.
Yeah.
And that exponential rate of change, it's just baked into our DNA now. It's not slowing down.
Yeah.
Being at the center of that pace, it's a real privilege.
So,
But yeah, it definitely comes with new challenges, new responsibilities as the company's scale and global impact have grown so much.
so as we wrap up this deep dive, here's something for you, our listeners, to think about. Given this relentless pace, this accelerating shift towards designing entire complex systems, not just chips, how might your own everyday world, your phone, your car, your healthcare, be fundamentally re-architected in the next, say, 10 years? Not just by what technology makes possible, but by what these underlying design tools make economically viable to build at scale. And maybe what seemingly impossible physics or complexity barriers will engineers using tools like these overcome next, and how might that reshape our whole perception of what humanity can actually achieve?